Now we come to the theoretical concept of sampling distributions. Imagine that you have a population which has a size, it has a mean, and it has a variance. And you take a sample from this population of a certain size and calculate the sample mean. And the sample mean is an estimate of the population mean. Now we're going to do a thought experiment. Imagine that you take a large number of samples from this population, each of the same size. Each sample is drawn with a replacement, so the population doesn't change. And you calculate the sample mean for each of these samples. Now you will have large estimates of the population mean that will all be equally good, but they will all be slightly different from each other. Actually, in theory, you draw an infinite number of samples, so you will have an infinite number of estimates of the population mean. Now imagine you plot all of these means in a distribution. This plot is called a sampling distribution. And this distribution will also have a mean of means, so to say. And what do you think this mean will be? Well, theory predicts that it will be exactly the same as a population mean. X bar bar equals mu. And that is pretty intuitive. This sampling distribution will also have a variance. Now, how large will that be? Well, that depends, of course, on the population variance. If the population variance is very large, it will be more difficult to get a good estimate of the population mean. So the sample means will differ a lot from each other, and the variance of the sampling distribution will be larger. The variance of the sampling distribution also depends on the size of the samples. The larger the sample size is, the better the estimate of the population mean will be. The means will be closer to each other, and the variance of the sampling distribution will be smaller. This relationship theoretically looks like this. The variance of the sampling distribution is calculated by the variance of the population divided by the sample size. We will have a closer look at this looking at a simulation study. And this simulation study is made in Microsoft Excel, so if you are interested in these kinds of things, you can easily make one on your own. So we start out with a population which has a mean of 3 and it has a variance of 6. And as you can see, this population is not normally distributed at all. So in the simulation, we drew 15,000 samples, each of the sample size 3, so a very small sample size. Calculated the mean of each sample and plotted these means in a sampling distribution. And what you can see is that the mean of this sampling distribution is pretty close to the population mean. It's not exactly the same because this is a simulation study, not theory, but it's close enough. We also have the variance of the sampling distribution. And now, what did we expect this to be? Well, we expected it to be the population variance divided by the sample size. So in this case, 6 divided by 3, which is 2. So the variance of our sampling distribution is pretty close to 2. Now what happens if we increase the sample size? And this sample is very small. We increase the sample size to 30 and we do the same thing. We make a sampling distribution. And we see that this mean of the sampling distribution is still pretty close to the population mean, but the variance has become much smaller than it was here. What did we expect? We expected 6 divided by 30, that is 0.2. So we're very close to what we theoretically expect. What you should also note is that this sampling distribution looks very normally distributed. This phenomenon is called the central limit theorem. And the central limit theorem states that the sampling distribution of the mean of any variable will be normal or nearly normal if the sample size is large enough. And 30 is a large enough sample size. This fact that the theoretical sampling distribution becomes normally distributed when the sample size is large enough, even if the population wasn't normally distributed to start with, is a very important concept in statistical theory. In fact, it is the theory that many statistical tests are based upon. And just because it's so important, let's take a look at another similar simulation study. We have a population again with a mean of 10 and a variance of 33.33, and as you can see, this population is very, very far from normally distributed. So we do the same thing. We take 15,000 samples with a sample size of 3, and we see already the sampling distribution becomes more normally distributed. And with a sample size of 30, the sampling distribution becomes very nicely normally distributed, even though the initial population was nothing like normally distributed. And we also see that the means of the sampling distribution is pretty close to the population mean, and the variances are pretty much what we would expect from theory.